Welcome, everyone. We are at our one of the last sessions, and we're going to be talking about using secure and privacy preserving data-driven systems. And it is my pleasure to welcome Dr. Shagufta Manaz, who is an assistant professor of computer science at Dartmouth College. She has her PhD in computer science from Purdue University and is broadly interested in the areas of security, privacy, machine learning, and her research efforts develop novel machine learning techniques to protect data from different types of attacks. Attacks such as insider threats, ransomware attacks, and also enhancing the privacy and security of machine learning techniques and models. Her papers have been received in different areas as best paper awards like the Codify of 2017, EWSN of 2017. She's been selected as one of the top 100 computer science young researchers from all over the world. Was selected to attend the Heidelberg Lawrence Forum in 2018. Is a recipient of the Schlumberger Foundation Faculty for the Future Fellowship, has her master's in computer science from Purdue and a bachelor's in computer science and engineering from Bangladesh University of Engineering and Technology. And it is our pleasure to introduce her to us so that she can give us this presentation. Welcome.
Thank you so much for this very kind introduction. So yes, I'm very happy to be here. Thanks for having me. It's great to be a part of NSF Research Conference. And I'm excited to share my research with you and hope that I will have like more feedbacks and questions during the presentation and also at the end of the presentation. So all right, let me share my screen with you all. Can you see my screen?
Yes.
Okay, sounds good. So yes, the goal of the talk is to talk about the secure and privacy preserving data-driven systems and to encourage you to pursue research in this direction in future and to invite any questions you might have to how to start working in these directions and so on. So feel free to stop me during the presentation and ask questions. That would be great. I mean, a great part of that is the biggest achievement from this talk, I would guess. All right, so today we will talk about this intersection among security, privacy, and machine learning. So there are cool works in this intersection. So I will talk about mainly these two directions. The first one is machine learning for security. That is, how can we use machine learning to improve security in different security applications? And the second part of the talk would be how to improve the privacy and security of machine learning. So for the first part, I will talk about the ransomware threats. That is a kind of malware that when it encrypts, when it affects your system, it encrypts your files and then asks for a ransom. That's why it is called ransomware. And we will go more into the details, but for now, just a high-level overview. And the second work is insider threats. That is maybe some employee within the organization, if they are stealing the data or misusing the data that they have or access to. So how to prevent this kind of insider threats. So how can we apply machine learning to identify this kind of ransomware threats and insider threats and prevent from losing this sensitive data. And the second part is privacy and security for machine learning. In this area of machine learning, I mean, is in the area where the data that is being used for machine learning is very privacy sensitive. For example, this could be health data or financial data. So when we apply machine learning to extract knowledge from this kind of data, how can you make sure that the privacy of the data is preserved? That could belong to the individuals, that could belong to companies, so on. So I will talk about two works in this domain. That is how to identify anomalies in sensitive data without compromising the privacy of the data. And also I will talk about this other work, that is when there are multiple parties who own some part of the data and want to collaborate to train a machine learning model, then how to preserve the privacy of each individual party. So this is a high-level overview, and if there is any question at that point, all right, if not, then I can move forward. So first, I will talk about this ransomware, the work from a conference in late 2018. So how can we detect the ransomware at real time, uh, specifically targeting the cryptographic ransomware? So we will just take a look at it more. Okay, so this is how it looks when your machine is affected by a ransomware. So you can see that this is the message. It says that your files have been encrypted, and it gives also you the instructions that how can you recover your files. And the thing is that you have to pay a ransom in the form of Bitcoin so that the attacker cannot be tracked. And only then you can get access back to your files. So they don't take your files away. They just affect your system. They encrypt your files using some encryption mechanisms, like which uses some keys, and then they force you to pay if you want to get your files back. So if this screen gets to your get to your computer screen, then the only thing that you're left to is you have to pay some money, and then they will give you the key that they used to encrypt the files so that you can decrypt the files, and now the files are available to you again. So this ransomware threats um, focus to get the availability part of security. So maybe you know that security has three parts, that is confidentiality, integrity, and availability. So as you can see that the ransomware affects the availability part of security, where you lose access to your data, and to just recover the files that is owned by you, you have to pay the ransom to the attacker. Okay, so let's see that who are the victims. So as you can see that hospitals have been a continuous target of this kind of ransomware attacks. Why is that? Because this is a very sensitive institution. So they have a lot of data, and if the attackers somehow um, successfully attack with this ransomware, there is high chance that the hospitals would pay the ransom to get their data back. There are other instances, for example, San Francisco rail systems, shipping companies. And as you can see that this ransomware costs like billions of dollars of damage to individuals, to companies, to hospitals, so these institutions. So this is the goal of this work, to identify this kind of ransomware in a very early stage so that they cannot encrypt the files that are very important to you. And I will discuss about how we achieve that goal. All right, so what is the challenge here? If you can see that there are different families of ransomware, for example, Petaya, CryptoLocker, and so on. So the ransomwares are very different. So when you want to come up with a solution that can stop them from encrypting your data, you have to come up with a unified approach. But again, as I said, that there are different kinds of ransomware. So let's take a look into the details. So for example, you have this file. So some of the ransomware would just read it, encrypt it, and write to the file and close the file. So it's just an overwrite of your file. And then some ransomware, what they do is that they read a file, they create a new file in your file system, and then deletes the original file. Some other ransomware, what they do is that they read your file, they write to a new file, the encrypted content, and then they overwrite your original file to be just empty. So as you can see that you are left with these F prime files, which are encrypted, and you don't anymore have access to your original file F. So as you can see, there are different approaches that this ransomware takes, and it is really difficult to identify a single pattern that they use to encrypt their files. So how can we come up with a solution that can handle these different kinds of ransomware? So let's take a look at the limitations of existing solutions. So let's say that backing up all your files could be a solution, right? So you have a second version of all your files in some cloud, and then if the ransomware attacks, you don't have to pay them, but you can just download all your files from the cloud storage. But if you see this example that this US hospital paid 55,000 to hackers after ransomware attack, you can see that they paid it despite having backups available. So why is that? Because hospitals they need to return to their normal operations as soon as possible. So it was not possible for them to back up the data that they have in the cloud, because it would take significant amount of time. And also the backup might not have the most recent data that they generated in their hospitals. So they decided to pay it even if they had all the data in their backup. So in many situations, this might not be the foolproof solution, that backing up your storage and just retrieve them when your system is attacked by ransomware. So this solution has limitations. Also, there are solutions that only focus on building post-encryption techniques. So let's say that your files have been encrypted and the attacker is looking for the ransom, but then how to retrieve the files without paying the ransom. There have been research in that part, but these solutions are very limited. They can maybe recover the files without paying the ransom in less than 1% cases. So what about the other 99% cases where you don't have all the tools to decrypt the files without paying the ransom? So these have limitations. And also there are some solutions that can detect the ransomware only in an offline fashion, that is not in real time. So if you can have maybe if you have some samples of some executables, and then you want to see that whether this is a ransomware or just a benign file, then you can do those experiments in a virtual machine, or in a very like a controlled environment. But that does not take care of the real time case of ransomware detection. Also, there are limitations in terms of accuracy in the existing work, because in those cases, maybe they miss some of the ransomware and identify them as just good files, or maybe they just identify a good process as a ransomware. So there are these false positives and false negatives in terms of their performance. And finally, the detection could be very slow. That is, um, uh, at the time when they detected the ransomware, it is too late, because a lot of files have already been encrypted in your system. So the goal of our research was twofold. The first one is we wanted to make sure that we want to identify the ransomware processes in real time, so that they cannot damage a significant number of files. And also the second goal that we had is we should have a significant amount of accuracy. That is, our classifier is not classifying some good file as ransomware and vice versa. Okay, so let's take a look at how this ransomware encrypts the files. So let's say that this is a command and control server, and they generate this public private key pair. So when they affect a file system, they create a unique key for each of these files and encrypt these files. And then they send the public part of their key pair and encrypt all the keys with that key. So finally, this other part of the key, that is the private part of the key, this is what they sell for ransom. So when you pay the ransom, they give you this private part of the key, and so that you can use that key to decrypt all your files. Can you see my mouse pointer? Okay.
Yes.
All right, that's good. Thank you. So this key is the private part of the key, and this is what they sell for ransom. Okay. So let's take a look at the overview of our Roger solution. So these are the IO requests sent by these processes. That could be any process that is running on your system. So all these IO requests have to go through this IO scheduler. So this is the IO request queue, and it goes through this IO scheduler before it hits the file system and really execute the requests such as read file, write file, or open file, this kind of operations. So what we do is that we intercept this IO request. So when the processes are making a request to read or write to different files in the file system, we intercept these requests, and then we parse all these requests and feed those to these three monitoring modules. So again, this IRP means IO request packet. So each IO request is packaged in this packets, and we get this information using this IRP logger. Okay. So there are three monitoring modules. One is the process monitoring, that is to identify whether this process is a ransomware or not. So we monitor the process itself. The second monitoring is file change monitoring, because as I say that ransomware encrypts your files. That means that they make changes to your files, right? So we also monitor that whether some file is being changed significantly, because when it encrypts, it means that it is significant change in a file. Previously, it was some text, and now after encryption, it's encrypted text, which means that there is a lot of random characters and letters in your file. So that's why we employ this file change monitoring. And finally, we have this decoy monitoring module that I will talk about it later in details. So the goal of these three monitoring modules is the first one of the two that I mentioned in the previous slide, that is real-time detection and accuracy. So the goal of these three monitoring modules is to make sure that we can identify the ransomware in real time. And then I have another module that is crypto API hooking. And the goal of this hooking is accuracy. That is the second one that I described in the previous slide. And then with all these three modules, four modules, we try to identify whether a process is a ransomware or not. If these modules decide that this process is a ransomware, we stop it. We stop the process right away so that it cannot access the file systems anymore and damage the files. All right. So we'll first describe these three modules, and then we will move to the second part of it, that is to ensure the accuracy. All right. So let's take a look at the process monitoring. So the key idea that we use in this monitoring module is that it takes very little time. So from infection to encryption. So when your system is infected by a ransomware, it takes in average only 3 seconds for the ransomware to start encrypting your files. So they typically attempt to encrypt files rapidly. So here are some examples of some ransomware. For example, Tesla Crypt, it takes only 28 seconds before they show you the message that I showed at the beginning of the talk, that your files have been encrypted. Now, how to recover your files? You have to pay this amount of money. So it takes only 28 seconds for this ransomware, and even for this Chimera ransomware, it takes only 18 seconds before it shows that message on your screen. So we leverage this exploit this property of ransomware that they encrypt the files very rapidly, which means that whenever they affect your system, they send a lot of IO requests to the file system because they want to encrypt as much as files as possible. So why does they do that? As I say, that they want to maximize the damage. And also the second advantage that they have for this fast encryption is that they want to minimize their runtime. So if there is a ransomware that is encrypting the files for a very long time, very slowly, then it might get caught and it might not be able to encrypt a significant number of files, so that the user is encouraged to pay the ransom. So these are the two reasons, maximizing damage and minimizing the runtime. These are the two reasons that they attempt to encrypt the data very rapidly. All right. So what we do is that we, as I said, that we log the IO request packets, and the advantage of this is that these requests are sent well ahead of actual file operations. So for example, if they want to write to a file, we log the write request well ahead of the actual write operation. So this is the property that we exploit. So let's take a look at what are the features that we look. For example, given a process, we see what is the frequency of different kinds of file operations. When they send this request, what are the frequency for example, for the write request, read, open, create, and the different kinds of file operations. So we compute the frequency of this request for each file type operation for each process that are running on the system. And if we see that there is a process that has significantly high frequency of sending this kind of IO request, then it gives an indication that this process is doing something wrong. So for this, we built a machine learning classifier that can identify, given this frequency of the process, whether it's a ransomware or a benign process. So we take 261 processes, including both benign and malicious ones. Malicious means some ransomware processes, and we build a classifier. So when we build the classifier, we have to collect some training data. So we use some good processes and also some ransomware processes and see how they send these IO request packets. So we built 4 classifiers with knife-based, logistic regression, decision tree, and random forest. And these are the results for each of this machine learning classifier. As you can see that for knife-based, the result is not too good because it has the assumption of class independence property, for which it does not perform very good because the read requests has relation with the write requests. So this independence class property assumption makes the accuracy of knife base to drop. Also, logistic regression they can only learn a linear boundary between ransomware and good processes, so that they also fail to get a very good accuracy. So we saw that for decision tree and random forest, the results are good, but again, we picked random forest as the final classifier because it is more scalable and it is less prone to overfitting. So finally, we trained a machine learning classifier with random forest to identify whether a process is benign or a ransomware one, given that how frequently they request different IO operations, for example, read or write operations. Okay, so let's take a look at the file change monitoring. So as I said that when the ransomware encrypts your files, it means that it makes significant changes in your files. So previously it was a text file which had some structured data, but then after encryption, it becomes really like very different from its previous version. So we use this similarity comparison. So how much the file is changed. We use this hash function, and so it gives a value between 0 and 100. If it's like near 0, it means that the file has been changed a lot. And if the files are exactly same, you get a value of 100. So this is how we understand after each write to a file that whether the file has been changed significantly. The second one is entropy. As I said that if the file is encrypted, it means like it looks like a garbage, and then it gets a very high entropy value, for example, 8. So after each write operation, we compute the entropy of the file. If it is near 0, it means that it's not in an encrypted form. And if it's near 8, it means that there is a high chance that the file has been encrypted. And finally, we also take a look at the file type because for many ransomware families, what they do is that after they encrypt the file, they change the file type. For example, from PDF, they change it to some like garbage file type extension. So after each write operation, there could be thousands of write operations in your computer. So we want to identify which write operation we have to look closer. So if we see that it has been changed significantly, the entropy has gone very high, or the file type extension has changed, we need to look into the details. So these are the metrics that we use to monitor every file change that happens in your system. And finally, decoy monitoring. So decoy means some traps. So let's say that this is the file system with all the good files. And then what we do is that we inject some more files in the system which work as decoy, that is the trap files. So in normal operations, the users would not touch or write to those files, right? So for example, in your file system, you know that this is a file that you don't generally use, right? So the red ones here. So these are the decoy files. But if some process tries to write to those files, it gives a very strong indication that that process is doing something wrong. It should not, that it should not do, right? So we deploy these decoy or trap files in the file system and monitor whether a process is trying to make changes to those files. So as soon as a process tries to write to these files, we can identify that as a malicious process, right? Because no process in normal situation should access or should write to those files. All right. So we also make sure that the decoy files do not become too old, because some of the ransomware are very intelligent. So they only encrypt the files that have been used, that have been changed very recently. So we also make sure that we update these decoy files in a regular fashion. For example, every day we make some changes to that, um, with a controlled process, so that the process itself is not flagged as a ransomware, so that the ransomware is equally interested to these files, similar to the other files in the file system. And also, um, we make sure that the names of these decoy files are similar to the ones in the same directory, so that it is not readily identifiable as a decoy file. And also, the size of the files, we vary it from 1 kilobyte to 5 megabytes. It's a random size in between this range, um, so that if you keep all your decoy files like 5 kilobytes, it gives some filtering advantage for the ransomware, right? So we vary the size of the files. And also, for the types, we use very normal files, for example, text, document files, PDF files. So there is an important thing to note is that ransomware always tries to encrypt the user files. They don't attack the system files. They attack these PDF files, document files, PowerPoint files, which are very important to the user, which is not recoverable by just reinstalling your system. So these are some of the files that the user created, and this could be images that the user does not want to lose, right? So we keep the extensions of these files as like text, PDF, so that these are equally attractive to the ransomware. So the first advantage of this decoy monitoring is that it can readily identify a ransomware process. So as soon as it tries to write to a decoy file, it can flag that process. And also it could delay the encryption of other real files, because if you have a significant amount of decoy files in your system, for example, one decoy file in each directory in your file system, there is a high chance that they will also touch one of those decoy files when they are trying to encrypt. So these are the two advantages. We also saw that for some of the ransomware, that is these three ransomware that we found, Mamba, Pitaya, and Masno, they did not affect the the decoy files, but some predefined list of files. And but I want to again say that we have this other two monitoring that are described in the previous slides, like process monitoring and file change monitoring, that still could identify these special ransomware samples, Mamba, Pitaya, and Masu, even if the decoy monitoring uh, module failed, because they did not affect the decoy files, but only a predefined list of files. All right. So we have already took a look at these three monitoring modules, and now I will move to this crypto API hooking part. That is to ensure that when we are classifying a ransomware or a benign process, we are not having a lot of false positives or false negatives. Okay, so let's take a look at this module. Okay, so for this, we built an encryption tool using Crypto API, which is a Windows system provided API for Windows app developers, so that they can use the functions that is provided by this API and do not have to worry about the details of the crypto operations. So they can just use this API and encrypt or decrypt the files, which are for good use, for benign processes. Okay, so what we do is that we place a hook in the crypt encrypt function. So let's say that this is a function, and then we place a hook there which forces the program to jump to this module, and we then extract all the related parameters that is done by the script encrypt function. For example, the key, the algorithm, the file which is being encrypted, the process, and timestamp. So why do we do that? You might want to encrypt some of your files. For example, you're traveling and you want to encrypt your files to make sure that if during traveling you lose access, I mean, you lost your I mean, there could be many situations. For example, someone could steal your machine. Then you want to encrypt your files, and so that even if it's lost, no one can get access. So there are many good uses of encryption, many use cases that why you want to encrypt the files. So when the user himself or herself encrypts the file, we don't want to flag those as ransomware because these are good encryption. So we use this tool, and whenever the user encrypts the files using this tool for a good reason, we don't want to flag that, but we keep a log of these operations, that the good encryption by the users, and then we so that we have access to the key, the file information and timestamp and so on, and we store all this information, all these tuples in a database, and again we keep it encrypted using a password so that the ransomware cannot have access to it. Okay, so the goal of this crypto API hooking module is that we don't want to flag good encryptions as ransomware. So finally, the advantage of this module is that we want to remove the false positives. That is what I just said, that we don't want to flag good encryptions as ransomware encryptions. And another advantage that came as a byproduct is that we saw some of the ransomware families, that's Locky, CryptoWall, and CryptoLocker, they used the same API to encrypt the files. So when they encrypt the files, we already have all the key information for each of the files. So what happened in those cases is that since we are hooking all these script encrypt functions and we are keeping all this information, we could retrieve the files without paying the ransom. So that was not the goal, but again, it was helpful because we could retrieve the files even without paying the ransom because they used the same API to encrypt the files for their ransomware encryption. But that is not true for all the ransomware because some ransomware might have their own cryptographic functions, own cryptographic libraries, and they don't use some predefined or existing cryptographic library. So yes, let's take a look at the highlights. We used 9 ransomware samples for building the machine learning classifier for process monitoring that I mentioned in the previous in some of the previous slides, and then we use 5 more ransomware families for testing. So we take 14 most prevalent ransomware families for all our experiments, and these are some of the results. So let's take a look at the number of requests that could be sent by the ransomware before we could stop them from accessing the file system. So if you can see that with decoy and without decoy, so we have experiment results when we deploy the decoy files and without the decoy files. As you can see that for this Locky, Jigsaw, Tesla Crypt, CryptoWall, Radament, and Rex, these ransomware samples, they could not, the first IO request, write request that they sent was to a decoy file. So we could readily identify those ransomware samples as malicious and stop them from encrypting a single file. So we didn't lose a single file for these ransomware samples. And for some other, for example, this one and this one, we saw some requests, but as I said that the actual file operations happen after a significant amount of time of the requests are sent. So you can see this these requests and readily stop them from doing the harm of encryption. All right, so let's take a quick look of the detection effectiveness. So the decoy monitoring module, it results in the fastest detection because as soon as the ransomware touches a decoy file, you can identify the ransomware. The second one is the process monitoring. It is faster than the file change monitoring because file change monitoring can identify a ransomware only after the file is encrypted, only after there is a significant change in the file. So, but the process monitoring can identify the ransomware even before the file changes have been done. But the disadvantage of this process monitoring is that it might have some false positive results because some other good process might be sending a lot of IO requests to the files, and uh, we might flag them as ransomware, but originally they are benign. And that's why we use this crypto API hooking that I just described in the last slide, that the goal of this hooking module is to remove the false positives. So I think that's the end of this first talk, that is ransomware. If there is any question, I'd be happy to take. If not, then I can move to the next slide that I will discuss the insider threat very quickly. So insider threat, as I said in the beginning, is that when an employee inside an organization tries to misuse the data that they have access to, then this is called the insider threat. So we can have the example of Target that happened in 2013, that some hacker got access to the payment card readers through a third-party HVAC vendor, and they stole 40 million credit card numbers. So that's huge compromise of security. So also, if you can see this example of Anthem, which is the, I think, second largest health insurance provider in US, there also have been this data breach there. So what happened is that an employee within Anthem, they emailed a file to his own email address that contained the very sensitive information of Anthem subscribers and Anthem members. For example, the names, their social security numbers. So this has been done by an insider within Anthem because he or she works within the Anthem organization, right? So how do we handle this kind of malicious insiders? And it can also happen that the insider is not malicious, but he or she can become compromised. So how is that? For example, an outsider can send a phishing email to the insider who is within the organization. And if the employee within the organization falls for this, like clicks some link and then gives away his or her credentials to the outsider, then the outsider can establish a direct connection to the sensitive files within the organization. So this is the case of compromised insider. So the insider is not malicious, but he or she is compromised. So in this way, it is also possible to gain a lot of information about the sensitive data that is within the organization. So the challenge here is that there is nothing abnormal, right? So um, I would not say that nothing abnormal, but the employee already has access to these files, right? So it's not something that they are accessing the files without having permission. They already have the permission. So how can we identify that something malicious or something abnormal is going on? So there are a lot of techniques, for example, access control, encryption, and authentication to save data from outsiders. But these are not enough because we are now dealing with the insider threat. That is someone who already has access, who already knows the keys, or who is already authenticated because the outsider has already gained access to their credentials, right? So how can we prevent this kind of threats? So here comes the necessity of anomaly detection techniques, because when some outsider gains access to some sensitive data in the organization, it's very it's expected that they don't know how to use the sensitive data. So they might be sending different, they might be doing something different, something very different than the actual actual employee within the organization. So there should be some anomaly in terms of the behavior patterns with the file systems. So I have a paper called Ghostbuster, fine-grained approach for anomaly detection in file system accesses. Though I'll not be going into the details of this work for this talk, because I have this other thread of privacy preserving machine learning. But just to give you an overview, that what we try to do is that we try to identify anomalous accesses that is out of context. So for example, if the actual user accesses the files A, B, C, and if, for example, there is a malicious outsider who somehow got access, they might be trying to access file, let's say that F. So that is very different. That is an access that is totally out of context. So we try to identify this kind of accesses that are totally out of context. And also we take a look at the anomalous frequency of file accesses. And finally, which part of the files are being accessed. So we look at the block level accesses. So each file is divided into blocks in the file system. So we also try to identify that which size or segment of the file is being accessed and whether it's very anomalous than the normal users accesses. So this is a high level overview of this work, but if you're interested, you can always take a look at the paper. And if you have any questions, I'll be available by email. You can reach out to me after this talk today. Okay, so I have talked about this first one, the ROGERD, and also I have given you some idea about insider threats. Now we'll move on to this privacy preserving real-time anomaly detection using edge computing. And
Dr. Menas?
yes.
Before we move on, Marie had a question about
Sure.
the when we were talking about the ransomware, and wanted to know what the effects of being able to take care of it, how much it would slow down the system.
That's a great question. So we use this IRP logger that logs all the IO request packets, and it has an overhead of only 1% CPU usage. And so that we run continuously to get the logs. And the other modules also has a very low impact in terms of CPU cycles. It is even less than 1%. So in total, we have less than 2% of CPU overhead when we are monitoring these things. And also, if you look at the decoy monitoring, you just have to update the files once a day. And if there is any access to a decoy file, you have to flag it. Otherwise, there is nothing that takes to continuously monitor. For the process monitoring, we compute the frequency of different file access requests in a 3-second window. So that has some overhead, and that's what I say, that 2%. It's not more than that. So we for example, we look at the file changes. So how much the file is changed only if there is a file write operation. Otherwise, we don't have to do anything, right? So it's not a heavyweight monitoring, but it's very lightweight. And as I said, that it is less than 2% in terms of CPU usage overhead. Does that answer your question? Was it from Maria? Okay, yes.
It was from Marie, yes.
Okay. All right. Thank you for the question. All right. Is there any more?
I would just ask everyone, please go ahead, add to the chat, and when there's a pause, I will interject and make sure that Dr. Menas is aware of your question.
Sure. Yeah, that would be
Thank
great.
you, Marie.
Thank you. All right. So now I'll move into this second part of this talk, that is privacy preserving real-time anomaly detection and using edge computing. So, all right. So as we have just seen, that these anomaly detection techniques are very useful. So it's now almost everywhere. For example, if you have a smartwatch, it might have some anomaly detection technique so that when the owner of this watch falls, they can even call 911 to rescue, to initiate rescue operations. So these anomaly detection techniques have been used in many different devices. For example, your home security system, as I said, your smartwatch, or industrial IoT. So when we want to identify this kind of anomalies and respond to it, in some cases, it is very important that we preserve the privacy, because if it's a medical device, you don't want to share your data, continuous data, to some third party. if it's an industry, then they might not want to share their critical infrastructure information with some third-party service provider, right? So how can we detect the anomalies in this kind of sensitive data, sensitive, so where it involves this sensitive data without compromising the privacy of the users. So for example, your home system security, you don't want the third-party service provider to always monitor your camera that is in front of your like front door or inside your home, right? So how can we make sure that we can identify the anomalies but without giving away the privacy option? So if you look, there are many services, third-party services, for example, Google Analytics, Microsoft Azure, some specific companies that are that have their focus on anomaly detection. So other than this Microsoft or Google, so they already provide this kind of services that if you give your data in plain text, in clear format, they can monitor the data and tell you that, yes, there is an anomaly in your data. But the problem is that they do not take care of privacy at all. Because these systems, when we build this kind of anomaly detection or any other machine learning systems, we don't think about privacy. So it is an afterthought. We always think about the functionality, that how well we can identify the anomalies or how well we can extract the knowledge from the data. But privacy is always an afterthought. So so this is the limitation of this existing solutions, third-party service providers. So the goal of this work was to come up with a solution that also thinks about the privacy and preserve the privacy while also getting the anomaly detection service. Okay, so sorry. Can I? How to close it? Sorry. It was all right. Can you see it now? Is it good?
Traditional privacy preserving machine
Okay,
learning
okay.
solutions. Yes.
Yes, yes. So I had some other window came up in my my screen. So I just wanted to make sure that it's not affecting your view too. All right, so I have removed that. So as I was talking about these third-party service providers, and the limitation, another limitation is that there exist a lot of privacy preserving machine learning solutions, but if you see the specific application we are talking about, that is anomaly detection, it has the requirement of being real time. So this traditional privacy preserving machine learning solutions, what they do is that they collect the data for a long time and then pre-process the data and apply very complex cryptographic solutions, and they can do this machine learning in an offline fashion. So it's not, so it cannot handle the real-time requirement of anomaly detection. So our goal here is to handle this both requirements, that we need to have the privacy, and also we want to get the advantage of this utility, that is we want to do it in real time, and that's why we cannot use these traditional ones, right? So I will show that how we can do that in the next few slides. Okay, let's see that if there are some devices, for example, those could be your home sensor devices, or you know, the smoke detectors, and many other devices. It could be in some industrial settings, it could be some health devices. So I will just show you some studies for different cases. So if you want to do all this anomaly detection computation in your device, so you do everything in your device. So what happens in that case is that you don't have to get service from the third-party service providers, which saves your privacy here. So you are good in terms of privacy, but in terms of latency, it takes a long amount of time, because the devices that we use, the small devices, they have their limitations in terms of computation, in terms of storage. So if you want to do everything in the devices, it takes like higher latency. And also some devices might have storage limitations. They cannot log historical data because they have very limited storage. And also there could be like battery depletion issues. So they might get out of charge if you want to do all the computations in the devices. So that's why we have uh, these third-party service providers, right? So the second solution could be you do everything in your device, but then to solve the storage problem, you send the encrypted version of the data to some server. So in that case, you solve the storage issue because now you are doing all the computations in your device, and then you are encrypting the data, and you are giving all the data to some server in an encrypted form. So your privacy is preserved because you're sharing only the encrypted data. But again, as you can see, that you're doing all the computations in the device, and sending all the data to some edge server might take higher latency, right? And there is some computation cost, and it might also cause like battery drainage. So if you continuously connect to this edge server for storing your data, the battery issue is also another one. And this is the third solution that I just talked about. For example, this Google Analytics or Microsoft or some other third-party service providers. You can send your plain text data to them, plain text data sent to the edge server, right? So in that case, this edge servers has very high computation power. In that case, the latency comes down to like really low, so that you have that real-time anomaly detection. There is some communication cost, but again, you can solve the storage issues. But as I said, that this privacy is gone because you're sharing your data in plain text, so that these third-party service providers can work on your data and identify the anomalies in a very short time so that you can respond in the real time, right? So here is the advantage, that the latency is reduced because you are using high computational powers, but again, your privacy is lost. So all these three approaches have their own limitations. And we want to come up with a solution where we also have privacy, but less latency, less communication cost, and also where the storage problem is solved. So I will talk about it in the next few slides. Okay, so what are the challenges? As I say that there exists various complex cryptographic protocols, but it conflicts with our real-time requirement because if we involve with like various complex cryptographic protocols, it might take a long time um, to really get the result of the anomaly detection. There is also this differential privacy techniques that exist to give differential privacy to the data of the owner, but there is a trade-off between accuracy and the privacy. So it's not a good solution if there is just one owner. Differential privacy could be good where a lot of individuals are coming and giving their data, and you provide this differential privacy. But it's not the case of the scenario that I'm talking about, where there is one single owner of the data and they want to preserve the privacy while also getting the real-time anomaly detection service. And also, there could be different kinds of anomalies, for example, point anomalies, contextual anomalies, or collective anomalies. So how do we handle these different kinds of anomalies with a single algorithm? All right. So this is a bit of math, but I just want to go over this very quickly. That is, we assume that data is normally distributed and it fits into a Gaussian distribution. So let's say that let's see that the data has this kind of distribution where the mean is mu and there is a variance. So how do we calculate that? What is the anomaly score of the data? So for example, if x0 is the point, this is the normality score, and if the point goes away from the mean, that is mu, it has less normality. So you can see that this is how we compute the anomaly score, and you will use this Q function to compute this anomaly score. So Q function gives you the normality score that is here shown by the shaded region, and then the anomaly score is just the opposite of this, that is 1 minus Q function. And just to give you a more detailed overview, that we do this in a moving wind analysis. So given a point, we identify whether it's an anomalous or point or not by looking at the recent past history. So we do it using this moving window analysis. So and also this kind of anomaly detection could be used in many complex scenarios, such as graph anomaly detection to identify whether in a very dense network there is any anomalous communication between two nodes. So this simple anomaly detection algorithm could be used in various complex situations too. So this is one of the most widely used anomaly detection algorithm, and we targeted this algorithm for our implementation. Okay, as I said that we cannot use very complex cryptographic constructs for our approach. So we designed a very lightweight encryption scheme that is a symmetric encryption scheme. So if you this is m is the actual value, k is the key, and eta is a nonce, and the computation is very lightweight. So this is a new encryption scheme that we designed to support this to support this real-time requirement, so that the encryption itself is very lightweight, and it has some additive homomorphism capability. That is, if you add the encrypted versions of two messages, it is equal to the encrypted version of addition of these two messages. So this is useful in our case, because when we do this moving window analysis, we want to get a sum, or we get a sum of the recent past history, and we want to compare to that. So this is very important in our, so that we can also enable some operations in the encrypted domain, because now the third-party service provider will only have access to the encrypted data and not the plain text data. So how we can enable them to do some computations with the encrypted data, right? So that is why we use this additive homomorphism. Okay, so there is a comparison between our encryption scheme, that is this Trident encryption scheme, and also Pallier encryption scheme. And you can see that um, what is the latency of this new encryption scheme that we propose. This is very less, several magnitudes of, yes, I mean, they're lightweight in terms of the time required for encryption when compared to Pallier, which is a very popular encryption scheme. All right. And as I said, that we need to optimize the aggregation, because we are looking at the recent past history and computing the anomalies in a moving window basis. So if you want to compute on the C represents the encrypted values, right? And M is the actual value. So if you add a number of encrypted values in the encrypted domain and compute it, you can see that we make use of this telescoping series, right? So only two terms remain, so that it becomes really lightweight when you want to um, compute over this encrypted domain. So it's just, though it involves a lot of these terms, but eventually we use this telescoping series to reduce the computation overhead to a minimal one. So this is how we make this encryption very lightweight. And finally, the accuracy when we operate on this encrypted data is same as plain text. So as if you are doing all the computations in plain text. So that is why our whole privacy preserving scheme is better, performs better than differential privacy in terms of accuracy, because when you apply differential privacy, there is some compromise in terms of accuracy, right? Because you introduce a lot of noise. So we don't do that here, so that the accuracy remains same as if you are doing all the computations in the plain text data. And finally, we have a proof in the paper that this provides semantic security, that is, an adversary with polynomial time bounded capability cannot break the encryption scheme, so that we have a very strong security when we use this encryption scheme. All right, so let's take a look at how we use this encryption. So given that we are collecting the data from these sensors that are deployed in industry, our homes, or our smartwatches, these devices first encrypt the data, and then they also use some offsetting before it sends to the cloud server, right? So all the data are sent in an encrypted form, but as I said that we use additive homomorphism to enable the server, this edge server, to do some computations even on the encrypted data. So this is another step that is called offsetting, and I will just say describe now that why we do that. For example, you have this smart door, and whenever you approach to the door, there is a spike in the signals. So when you are giving the encrypted data to the server, you don't want this kind of spike to reflect on your encrypted data, because it gives the server the information that when you are entering to your home or when you're exiting your home, because in that times you are approaching to the door and there is a spike in your signal. So we use offsetting to make sure that this information is also hidden from the servers. And then, as I said, that this is an identity homomorphic encryption. So all the computations cannot be done in the encrypted domain, but some of them could be done. So whenever the server needs to do some computation that is not possible for the server to do, it sends some data back to these devices, and then they again send some intermediate results to the server. So that now the whole anomaly detection computation is distributed between the servers and the devices, but we can use the computation power of the server, and at the same time we can preserve the privacy, because the server cannot see anything in plain text, whether it is the actual data or the intermediate results. Everything here is encrypted by the devices, and the keys for this encryption only belong to the devices. It is never shared with the third-party service provider. Okay. So I will just show the results for collective anomaly detection because it subsumes the point and contextual anomalies. So let's say that this is the normal data, and we want to identify if there is any anomaly in the data. So if you see it closely, you can see that there are actually 5 different patterns. So there are multiple Gaussian distribution. So this is the first one, this is the second one, third one, fourth one, fifth one, and it repeats over the time. So you want to build 5 different models, 5 different Gaussian distribution models to identify any anomaly. But for example, if you used just one, what would happen? The average value would be something here, right? And this anomalous data would not be identified because this is very close to the average that we just learned, right? So this is the limitation of using just one Gaussian distribution. Okay, so here is the encrypted data after we apply our trident encryption that I just described in the previous slides. So as you can see that this is very different from the plain text. So the red is the plain text. So this is just a compressed version of the first plot here. So this is the plain text, and the gray lines show the encrypted values. So as you can see that these are very different from the plain text, right? But if you closely look, there is still a pattern that shows, for example, when the door is opened and when the door is closed, right? So that's why we use offsetting that I just talked about in the previous slide. And after the offsetting, there is no such trend that you can see here. So it's totally random. And the gray lines are the values that is available to the third-party service provider, and they cannot learn the actual values that is in red by seeing these gray lines or the encrypted data points. All right. Okay. So we will just take a look at the different examples. So the plain text data looks like this. As you can see that this is an anomaly. And when we compute the anomaly scores using this privacy preserving framework, you can see that for these points, the anomaly score is 100%, right? So this is the values that we compute using this privacy preserving framework. So we can identify these points as anomaly using our anomaly detection, privacy preserving anomaly detection framework. And also, for example, if there is a higher spike, this is also anomalous. And for this case also, we have this confidence that this data is anomalous with 100% confidence. For example, if there is no such that means that something is missing in the plain text data, and also we can identify these anomalous data points with 100% confidence. So these are different anomaly examples, and I just wanted to show that how the anomaly score that we compute using this privacy preserving framework gives the results. Okay, so if we go back to this study that we did, We now add our solution where we have um, this privacy that is now good, because now we are not sending the plain text data to the third party service providers, but we are also solving the storage issue. Now we have a little bit higher latency than the third case, where we were sending all the data in plain text, which compromised our privacy. But again, with some added latency and some added communication cost, we could achieve the privacy, and also we could reduce the latency from these high amounts to these low amounts. So if we look at some concrete results, so these are the results to identify anomalies on 100,000 data points. So if you look at the numbers, if you do all the computations in the device, I used a Raspberry Pi to do this experiments. So it took 716 seconds to identify the anomalies if you do everything in these resource constrained devices. But then if you, for example, used some third-party service provider, you could identify the anomalies in 125 seconds for this 100,000 data points. There is some communication cost because you are sending all the data, but again, there is no privacy. And these are the results with our solution. That is, if you can see, there is some higher latency from 125 seconds to 145 seconds, because we are adding this encryption and some more communication to perform the anomaly detection computation. And also there is a little bit higher communication cost from 24 megabytes to 30 megabytes. But as you can see that it's not significantly high than the third column. But with this some overhead, you are giving the privacy of the data. That is, you are not sharing your data in plain text with the service providers. All right. So is there any question on this part of the work? All right. Sounds good. So I think we have some few more minutes. Then maybe we can quickly go through the third part of the work. Okay, so now I will describe another scenario where, for example, there are multiple parties and they want to build a machine learning model and extract useful knowledge. So for example, these hospitals have some data about the patients, and they want to build a machine learning model to learn, for example, what kind of dosage a patient might have, what could be the length of their stay. But each of the hospitals has limited amount of data. So if they try to learn a machine learning model from their own data, it might not be very accurate. So the more data you have, the more accurate the model is, right? So this is why the hospitals might be interested in collaborating with other hospitals so that they can come up with a good model with more useful knowledge. And the problem here is that since the hospital data is very privacy sensitive, there is this major privacy concern that they cannot share their data with some third-party service provider, right? So how can we solve this problem? So in this work, what we do is that all the data that belongs to the hospitals, they remain with the hospitals. So they are not sent to the server. What they do is that each individual hospital, they train their own models and they share only the encrypted local results with the service provider, so that when the model is built locally, they just learn some parameters and share the parameters, model parameters, with the server, and the server aggregates the parameters to come up with the global model. So, and this information is then shared with all the hospitals so that they can have a very good model, but without sharing their raw data with the third-party service providers. So I think we don't have a lot of time. Do we have to go?
We have a few questions.
Okay, sounds good.
We have
So
a
I will
few
not go
questions.
into the details of this work. This is a more, yeah. So let's take the questions first and then see if we have time.
Okay. Somebody asks, is RW Guard or the anomaly detection product or AP that is available?
The Robert work.
Mm-hmm.
So that is available. I can share. I'm not sure if it's shared as a public repository on GitHub, but I have it on my GitHub. So if the individual could knock me and I mean, send an email, I can share the GitHub repository with them.
Okay.
So
Okay.
yes, please just send me an email and I can share the link with you, the GitHub repository link.
Okay. And then another person asked, how long did it take to conduct this research? Is there abundant funding for research in cybersecurity?
So can you just repeat the question to make sure that I understand it?
Sure. How long did it take to conduct your research? I'm assuming, or I don't, Maria asked whether this was for both or just to one of the second portion. How long did it take to do your research?
Okay, yeah, that's a good question. So for the ransomware work, it took around, I would say, 1 full year. And I must say that it is a continuous process. So when I first worked on this project, I submitted to a conference and it did not go through for the first chance. So we got a lot of good feedback from the reviewers, and we again worked and addressed the reviews and submitted to a second conference. So I think it took almost a year to complete the project. And it applies to the second part of the work too, that is privacy preserving anomaly detection. And yeah, I think it's very important that we have this feedback loop. We submit to some conference and then get the feedback and work on that to improve the results. In terms of the funding, I would say that security is everywhere. So for example, network security, file security, and different kinds of security. So in terms of funding, I think that is a continuous process because, for example, patient-doctor relationship, right? So as long as you have new systems, new architectures, there will be this kind of like threats, new kinds of threats, and it's a continuous process. So yeah, I think funding is more available to security area than some others. So I cannot make a very strong statement on that, but I think that's a very important part of computer science research.
And then we have one more.
Sure.
This one dealt with what are some journals that take cybersecurity research papers?
Yes, so there are IEEE transactions, for example, TDSC. I can share some names in the chat box. Okay, let me.
And I believe ACM has some opportunities
ACM,
also.
Exactly. Yes, security and privacy. That's true.
Okay.